Okay, so it turns out that far beyond the Milky Way, we see billions of other galaxies scattered throughout space. And some look similar to our own galaxy, while others look quite different. Like, look at us. Look at this one. Differently looking from our own galaxy, Milky Way. Is this really a galaxy? Like, what is this? Is this part of the galaxy? Is it only one galaxy? Now we know that this is actually the result of interacting two or more galaxies thanks to gravity or gravitational forces. But you might make out some components in here. Maybe this is looking like a disk. Maybe this is looking like a bulge. Now, these things are blue, newly formed stars. Let's investigate. Let's look. And before that, let's recall a galaxy anatomy. And this is, the one with the capital G. So we're going to think about what we know about Milky Way. So remember, we have the disk component, right? Where the gas and the stars are in rough circular orbits. Remember, they kind of bob up and down, okay? And that's thanks to the gravity of the disk, right? So this is what the orbits of stars in the disk look like. And they're rather blue or white in color, right? And that's because there are energetic photons coming from young massive stars dominate light from the disk. While for the spheroid, which is both the bulge and the halo, the spheroidal component that kind of embraces the disk. The stars have those random orbits, right? Remember, we have the disk and we have the stars kind of rotating this way, and then we have those random orbits of stars in halo and also in the bulge. Remember, they do similar things. Yeah, and that's generally old stars. Old, that is low mass, right? And they are not as powerful in their fusion processes. That hydrogen that goes into helium and therefore not as hot. Vien's law, lower temperature, yellowish reddish color. So thinking and keeping in mind those basic two components, it's three, but two are very much the same, those spheroidal components. We were able to kind of put together three basic types of galaxies. And we identified, for example, in the tiny patch of sky, about a third of the size of the moon. And then Hubble Space Telescope found tens of thousands of galaxies in that tiny patch that looked empty, looked black before the Hubble Space Telescope looked into. Okay, so in an image like this, right, we actually are able to identify those three basic types. And what do we have? Number one, some galaxies that look all spheroid. So basically they have no disk component at all. And then there are the spiral and the barred spiral galaxies, and they have both a disk and a spheroidal. And then there are the ones that don't fit any of those previously presented molds. There is no spheroid, no disk. There is something that generally characterizes them, and that is they're generally made of young stars. There is a lot of blue light coming from those galaxies. So let's look at some examples of these different. Take this one, for example. Would you characterize that as, let's zoom in, obviously it's spiral galaxy. You see there is a bulge and then there is a disk component. They're both there. Let's look at this one now. What do you think? How about we zoom in? It looks like there is no disk, right? It's all a big bulge, basically only the spheroidal component. Let's look at another one. Let's see if we can find an irregular. Can you find a blob? That is, and I told you a few chapters ago that in this Hubble Deep Field, there are basically just two stars, the ones that have the spikes around them. All of the other points are galaxies, so just a reminder, right? These are stars, the only ones in this field. All the other ones are galaxies. So any speck you would look at is a galaxy. So here's one. Let's zoom in. Kind of irregular, wouldn't you say so? See any disk? Any kind of regular bulge-like structure? No. So therefore its name, irregular. Okay, so let's look at some other types. Okay, there are actually, of course, it's kind of hard to classify this big universe into three categories, universe of island universes, into just three categories. It turns out that some of the galaxies do not quite fit any of those three, but they're kind of variations of one of those three classes. Like, for example, this looks like a spiral galaxy, but it also has a region of concentrate with a lot of light coming from stars. So there is a bulge, there is a disk, therefore spiral, and we also see spiral arms. But there is also kind of a bar. It has a bar of stars, right? There are stars that orbit in kind of a highly concentrated number along that volume. That, looks like a bar. Therefore, they're barred spiral galaxies. How about this one? This is called the lenticular galaxy because it kind of looks like can you guess? A lentil. So it has a disk like a spiral galaxy, but much less dusty gas. So basically the bulge not as prominent, or it's much more extended. So it's kind of an intermediate, sort of like something in between a spiral and an elliptical. Here's another example, and this is actually a beautiful galaxy. It's quite famous for its beautiful shape. This is called the sombrero galaxy. Of course, these are names given by us. Look at it. Oh, it kind of looks like a sombrero. So what do we see here? We see many gas clouds in the disk, right? So the disk component. There are stars of all ages, but you also see quite prominent dust lanes here, and you know what that means: copious star formation, because those dust lanes are actually molecular clouds where stellar nurseries are. All right, and then there is the spheroidal component. Let me guide your eye. So it's kind of a bulge and halo all together. You have all stars, and it says here very few gas clouds. So basically no gas, no new stars forming. All the stars are formed in the disk. Just like we've seen, it happens in the Milky Way. So it turns out the spiral galaxies can actually be subclassified into subclasses, and it was Sir Edwin Hubble, the man after whom the telescope has been named. It was a name before it was a telescope. Okay, he was the scientist who tried to figure out what's going on in the universe. You know, he was one of the most prominent ones who asked fundamental questions about our universe and was actually able to provide some answers. You know, he and others, obviously, he's not the only one. He wanted to know how old the universe is, how big is it, how is it changing with time. And some of these questions might have seemed ridiculously speculative a century ago, and actually even Hubble gathered the data that he was able to put together with the telescopes that were available, mostly ground-based at the time. By the time he was running his own observations. But anyway, so one of the things that he did was kind of subclassify the spiral galaxies based on how prominent the spiral structure was, how prominent the central bulge, and he said, okay, we have an SA, a spiral of type A, that would be the one with large central bulge. So the disk is definitely present, but the bulge is very prominent. And then moving to the spiral of type B, for example, right, you see the bulge is a bit less noticeable, okay? And the spiral structure kind of becomes a bit looser, okay? And so this is one example, M81, and some other examples are M31, which is the Andromeda galaxy. So just as a side parenthesis, M comes from the Messier catalog. Okay, so we have M1, 2, 3, and so on. Messier was actually a French astronomer who basically put together a catalog of everything that looked fuzzy. Looking basically not like stars. He was particularly interested in finding comets, and he ended up classifying galaxies and clusters of stars and planetary nebulae. Although he didn't know, it was much before Hubble, the man, the scientist, took the catalog and looked again into these galaxies with new knowledge coming from the physics that evolved in the meantime. All right, so moving on, a type C, a spiral of type C would have weak or no bulge, very little bulge, and then the spiral structure now becomes very knotty, is not as tight as it was for the type A. So this is, for example, the name of the galaxy. This is coming from the new galaxy catalog. So this is where the NGC numbers come from. We're very very inspired with naming these galaxies. So as you can see, and you can keep going. Okay, we came up with some types, classes, subclasses of spiral, and then people thought, well, why don't we do that for the spirals with these are spirals with, can you all see there is something going on in basically all of these galaxies? I'm guiding your eyes with bars, and so these are going to be SB, the spiral barred galaxy of type A, B, C, and exactly like with the spiral galaxies, again, Sir Edwin Hubble classified the barred spirals according to the structure, the texture, the prominence of their central bulges, and the texture of their spiral arms. So you end up with the SBA, SBB, SBC, and so on. Here's another thing that I wanted to point out for all of you, and you probably can't make it up. This is an image of a galaxy, which is the galaxy is M81. Okay, the galaxy we've seen before, but these are images of this galaxy in different wavelengths. Okay, so we have different band passes, or wavelengths. Okay, so we have the UV image, and then we have the blue image here, and then we have the near infrared image, and you see they don't look alike. Like the edge of the galaxy is different. We actually see here knots of star forming regions, because we're basically seeing the UV photons coming from the very hot stars, the young, the massive stars. Okay, and then for example, in near infrared, we don't get to see those, right? Those young hot stars, they don't emit much in near infrared. They emit mostly in the UV. Okay, so here we see the lower mass stars, okay, and hot gas, and basically in infrared we see the gas and dust heated by the young, massive, hot stars. So these are all M81, Messier 81, so just one galaxy. And here is another series, M51, just another one of those galaxies. You see how different they are, right? Okay, so you see how the spiral arms, or the structure of the spiral arms, is clearly increasing, and it's much better defined as we move to shorter wavelengths, and that is, again, because of the star formation in the spiral arms. The rest of the galaxy, right? So this is material in between the spiral arms. So you see, different wavelengths actually reveal for us different things that happen in a certain galaxy, in just anywhere, actually any corner of the universe. So that's why it's very important for us to observe this universe with as many different eyes as possible. Okay, so we talked about the spiral galaxies, but remember, there are different types, okay? There are the elliptical galaxies, and this is a beautiful one. It's a very massive galaxy. Just as a reminder, right? This is the light that we see in these galaxies. It's coming from these stars that have quite a range of tilt and ellipticities, all kinds of orientations. Of the orbits. There's no disk, basically, in these elliptical galaxies. They're all spheroidal component, okay? And also, there is no interstellar gas. So basically, no molecular clouds, and therefore, no young star formation. Therefore, they're red or yellow color because we have older stellar population, right? And they're older. They lived for long time, and that means the stars are of lower masses, right? So basically here, no massive young stars, right? The massive stars, they die fast, remember? So they already died a long time ago. So basically, elliptical galaxies are like old, dying galaxies, which is quite a difference from what we see in the spiral galaxies, which are kind of booming of activity. They have lots of star formation happening in their disks. Okay, now it turns out there could be quite a few types or subtypes of the elliptical galaxies as well, as as again Sir Hubble thought of and looked and found a variety of things and said, well, why don't we look at how round or flattened they are, okay? So just like with the spiral galaxies, now we have some numbers actually associated with the E-type, the elliptical type, okay? And so the very round one would be of type E0, and then as it flattens, it becomes a higher number, flattened elliptical. And you go to, say, E10 is going to look like a cigar, kind of like that, right? Okay, but I also want to point out that there are projection effects involved, right? And so it's actually very hard to tell whether what we see is actually the true shape of those galaxies. So you can imagine you see something flattened, but you see it, from the position of the observer A, right? So you would gonna see an elliptical of type E0. However, if you look from the perspective of observer B, you would see it as a higher number. I don't know, an E6 type of elliptical. So things are not actually as clear-cut as we want to be. And the third type, or the one that actually doesn't fill any moles, so no disk, no bulge, no spheroidal component. Basically, not really a well-defined shape, okay? So no well-defined shape. What we see over and over again in these irregular galaxies is the blue-white color, and that indicates ongoing star formation. Remember that blue-white color, that means there are hot, high-energy photons, and they come from massive stars, the ones that were just born, right? And we know that because they don't live for long. They live very fast. They burn that hydrogen into helium in their cores very, very fast. Okay, so if we caught them, that means they were kind of born yesterday, of course, in astronomical times. So that irregular galaxy, that is a young thing. And then that would probably be a fourth type. There are the so-called peculiar galaxies. They really don't fit the mold, all right? Those usually are also called interacting or dancing if you want, and it's basically what's going to happen with Milky Way and Andromeda. Those are spiral galaxies, or M31 or Andromeda. And they are basically on a collision course towards one another. So in about 5 billion years, they will collide. And they will become one of these situations that we see in these beautiful pictures, right? There are beautiful tidal tails where the basically morphology of stars is disrupted by the gravitational interaction of the galaxy. So gravitationally interacting galaxies. We're actually going to talk some more about this in the next chapters. That would be later. So, Sir Edwin Hubble, he put together a classification, and then he thought, well, why not try to find the relationship between them? All right. And he put together what everybody knows as Hubble's tuning fork, because it kind of looks like a tuning fork. Some of you might be musicians, so you know better than others what that tuning fork might be. So anyway, Sir Edwin Hubble's classification of regular galaxies is shown in this tuning fork diagram. So here we have an elliptical galaxy classified by how flattened it appears, right? So the very circular one, very circular elliptical galaxy, so rounder, the roundest, and then flattens, and you get to the type of E 5, and then we see spirals. So these are spirals, and here are the barred spirals, and they are classified based on the texture of their spiral arms and the size of the central bulge, with larger or more pronounced bulges in this direction. So this is the SA and the SBA with the most pronounced bulges. And these are the loose one, right? These are the tightest spiral arms and most pronounced bulges. Okay, and in between there are these lenticular galaxies, the SOs, and maybe a barred lenticular would show up now and then. Okay, those that do not fit into the simple classification scheme of ellipticals versus spirals. So, Hubble put all this together into this famous tuning form diagram, and he believed that this is the representation of an evolutionary diagram. So we have here a galaxy classification, okay, and Hubble thought, well, maybe this is a representation, this is an evolutionary diagram. Hubble thought. But it turns out it is not. So initially, Hubble thought that maybe all of the galaxies start as ellipticals and they flatten because of their rotation, maybe kind of the same way a star is born, and then it becomes a disk, and then the spheroidal component becomes the bulge, and something happens, and some of them go on the branch without bars, and some of them go on the branch with bars. However, okay, it turns out that after some more observations, and that was after Hubble died, we learned that these are mostly old stars in these elliptical galaxies, and in the spiral galaxies, they're mostly young stars, or actually stars of all ages. Which is kind of weird, right? You don't start the galaxy with very old stars, which will evolve into the young ones, okay? So this is why this tuning fork is not an evolutionary diagram, okay? And we are going to, again, talk about what we learned about how galaxies form and evolve in the next. Another interesting thing about galaxies is that they gather in groups and clusters. And we already talked about that in the very first chapter when we looked at the structure of the universe, and we realized, well, okay, there are groups of galaxies, and the groups are in supergroups, and they are in parts of clusters. And now I want to tell you something new about these groups and clusters. It turns out that the different types of galaxies group differently. Like, for example, the elliptical galaxies are much more common in huge clusters of galaxies, and these are made of hundreds to thousands of galaxies. I don't know about you, but I read much easier. It's much pleasantly happening for me and understandable for me if I write numbers than words. But now you have it both ways. And the spiral galaxies, they tend to be either alone, so isolated, or in small groups of just a few, maybe a dozen at the most, right? And they're usually very close, or when they are close, then that gravitation, there are large distortions, there are tidal tails of stars whose morphology has been disrupted in a certain galaxy, and they're going to, they're kind of on a collision course. So they are gravitationally interacting. They're dancing, and as I said, I promise I'm going to show you some beautiful movies about how that happens, both simulations and real images. And to end this part of the chapter, here is actually real data. So we have every dot here is a galaxy, and SDSS stands for the Sloan Digital Sky Survey, and there is a dedicated telescope that produced data, ran this survey, just trying to map the geometry of the universe. And that is a relatively small telescope near Apache Point in New Mexico. So basically what we see here is a three-dimensional map of the distribution of the galaxies. We are here in the center of this map, so that is Earth, is in the center. And I said each point represents a galaxy, and a galaxy that typically contains about hundreds of billions of stars each. Reminders. Now the galaxies, that is each point here, are colored according to the ages of their stars, and you can see the redder ones. So these are redder galaxies. They're basically more strongly clustered. And they're made of older star. Redder. Older, cooler stars. The outer circle, that corresponds to a distance of about 2 billion light years. So, it kind of takes from here to here 2 billion years for light to travel. So this distance is 2 billion light years. Okay. Now the region in between the edges was not mapped by the SDSS. So these regions, this is where our own Milky Way, the disk, is, right? So it's going to be very, very hard to see through, right, because it obscures our view of the distant universe. But in a nutshell, any direction we look, we're going to see this cosmic web of galaxies. This is just a slice, right? This is a three-dimensional, but we just took a slice. And if you remember, we have the declination. It's just a tiny, like 1 degree or so slice, the wedge in the universe. So pretty neat, you see? There are many, many galaxies out there, and we're learning more and more about them every day.